The Kyoto Prize is an international award that honors individuals who have contributed significantly to the scientific, cultural, and spiritual betterment of humankind. It is given each year by the Inamori Foundation, which was founded in 1984 with the initial private funds of Dr. Kazuo Inamori, founder and chairman emeritus of Kyocera Corporation. The foundation awards 3 prizes annually in the following fields: advanced technology, basic sciences, and arts and philosophy. Each year, the Kyoto Prize Symposium is held in San Diego, California, with attendees arriving from all over the world. The annual 3-day event kicks off with a celebratory gala evening attended by many of San Diego's academic, corporate, and philanthropic leaders. Following a ceremonial procession, the gala audience learns about the current year's laureates' extraordinary achievements and then hears briefly from each. Another highlight of the evening is hearing from select recipients of the Kyoto Prize scholarships, which are funded by gala proceeds. These impressive high school students from San Diego and Tijuana have been inspired to pursue a college education in one of the 3 Kyoto Prize categories.
I would like to use my creative writing skills to help special needs kids, particularly through special education. My youngest brother, Remy, is a severely autistic and hemophiliac, so he's been the one to give me the desire and the empathy to help special needs students advocate for themselves and realize their potential to the fullest extent.
So I started a program on my robotics competition team at my school that brings programming outreach to, underserved and low-income middle and elementary schools around San Diego County.
As a freshman in high school, I co-founded 501c3 nonprofit All Girls STEM Society with the goal of creating a fun, encouraging, hands-on learning platform for girls to explore their interests in STEM. Since our founding in 2015, we've reached 2,800 participants from over 240 schools in 25 school districts across San Diego.
The symposium continues on the campuses of Point Loma Nazarene University and the University of California, San Diego. Free public presentations, lectures, and workshops by the latest Kyoto Prize laureates and esteemed scholars in the laureates' fields attract the region's best and brightest, as well as hundreds of high school students from Tijuana and Southern California. During their stay in San Diego, the laureates also meet with the symposium's key sponsors, providing these supporters the unique opportunity to interact with remarkable luminaries who have changed the world we live in. This prestigious event shines an international spotlight on San Diego, exemplified by our cities hosting each year's Kyoto Prize laureates, an honor which is shared outside of Japan only with Oxford University in Europe. Creating a global audience in the thousands for virtual presentations by the laureates. The more than 10,000 high school and college students from San Diego and Tijuana who have attended Kyoto Prize Symposia, and the awarding of close to $4 million in scholarships to high school students in the region. The Kyoto Prize Symposium elevates San Diego as a scientific, technology, and cultural leader, and helps reinforce our region's rising prominence on the world stage. In the words of Dr. Inamori, human beings have no higher calling than to strive for the greater good of humanity and society. San Diego is honored to play a role in this noble mission.
Kongo, 人類の未来は科学の発展と人類の精神的進化のバランスが取れて初めて安定したものになるであろうと確信をいたしております。
Kazuo Inamori believed that a human being has no higher calling than to strive for the greater good of humanity and the world. With that tenet, he established the Inamori Foundation in 1984 with an endowment of 20 billion yen of his own money. Since its inception in 1985, the Kyoto Prize, an international award named after Japan's original 1,000-year capital and cultural center, has been awarded to individuals and groups who have made extraordinary contributions in the fields of sciences, arts, technology, and philosophy.
願わくはこの京都賞がこの両面の今後の発展に大きく寄与し、新しい哲学的パラダイムの構築を促進するいささかの刺激剤となればこの上なく幸せに思っております。
Dr. Inamori believed that with the proper balance of scientific advancement and a deep spiritual understanding, the future of humanity would be bright and long-lasting. The Kyoto Prize is an extension of that belief and is now recognized as one of the most prestigious international prizes of its kind. The Inamori Foundation and the Kyoto Prize cement Kazuo Inamori's philanthropic legacy and will continue to do so throughout the future.
Good morning and welcome. On behalf of the University of California, San Diego, I'd like to welcome you to the campus as part of our annual Kyoto Prize Symposium. My name is Melanie Cruz. I'm an Associate Vice Chancellor here at the university. I have worked closely with the Kyoto Symposium organization for now nearly 2 decades and continue to count all the wonderful years we've spent together. We've worked really closely to bring some of the world's most gifted minds to share their impact on humanity, their personal journeys, seminal discoveries which our community in San Diego gets to hear about, and beyond. The spirit of collaboration and the interconnectedness and benefit to humanity shared by the Inamori Foundation and Dr. Inamori's legacy is closely aligned with the mission of UC San Diego. I would like to recognize and personally thank Inamori Foundation President Mrs. Inamori Kanazawa. I think she's here today. And we also have Senior Managing Executive Director, Mr. Hamono. Thank you to the other delegates for the Inamori Foundation who have traveled for Kyoto to be with us today for this special occasion. And I'd like to also thank our friends here from Kyocera International and Kyocera North America, headquartered here in San Diego, both founded by Dr. Inamori. We're very happy to have you on campus. I was talking yesterday to Rod Lanthorn, who let me know that Dr. Inamori founded Kyocera Corporation International when he was, 27 years old? What a remarkable man. But Kyocera Corporation was founded in 1959. And to give you a context, a year later, UC San Diego was born. So we share a common history in terms of being young, scrappy, and innovative, I think. During that time, UC San Diego has risen to one of the top 20 research universities in the world. As a public university, we are driving change to create access to education, advocate for society, propel economic growth, and solve complex problems that affect humanity. UC San Diego's rich portfolio of education, research, healthcare, public service, and innovation is closely aligned with what we do with the Kyoto Prize. I hope you enjoy your visit to campus, and please remember us as a place for education, employment, and healthcare needs. Our two entities have a common connection and a shared vision to improve humanity. This year, we will honor 3 extraordinary individuals who are the recipients of the Kyoto Prize, who embody that shared spirit. The Kyoto Prize laureates include Dr. Carver Mead, who we'll hear more about today, Dr. Brian Grenfell, a renowned biologist, and Dr. Zakar Hussain, a renowned musician. So we'll be hearing more from Dr. Mead today and the other laureates later on in the week. Today's program would not be possible without the leadership and advocacy from the Kyoto Symposium organization. Thank you, KSO directors. I believe Dick Davis is here, Rod Lanthorn. We also have members of the staff and leadership team, so thank you so much for making this possible. One of the most wonderful things about the Kyoto Prize Symposium is connecting these laureates with our communities in San Diego to learn a little bit more from our academic experts who will illustrate the contributions and the discoveries that have impacted humanity. Please welcome distinguished engineer, endowed shareholder, and dean of the largest engineering school on the West Coast, Dean Al Pisano.
Okay, good morning, everybody. I'm so happy and proud to be here today. It is an exceptional honor for the engineering school, the Jacobs School of Engineering, to be part of the hosting process for the Inamori Prize. And again, Dr. Carver Mead, thank you very much. We're so happy to be hosting you. When I was alerted that Dr. Mead was the prize winner, I was ecstatic. And then I knew there would be a challenge. Who is the perfect faculty member to work with Dr. Mead, make sure everything works well, and at the same time has an appreciation for the depth and the breadth of all the things that he has done. So it took maybe 4 milliseconds, maybe 5, because we actually have a spectacular faculty member, and I'm going to introduce that person today. This is Professor Andrew Kong. Now, Andrew Kong is what you would call an EDA guru, where EDA stands for Electronic Design Automation. He works in PDKs, Program Development Kits, of all kinds of foundries. So here's our faculty member that really knows how the fab gets done and the importance and value of the layout tools. And so without any further ado, Andrew, would you please come to the podium? I'm happy to introduce you to our wonderful audience. Thank you.
Wow. Thank you, Dean Pisano. It's very humbling to serve as the faculty host for today's laureate. Semiconductor technology has transformed our world, and this technology rests on many foundational advances made by Professor Carver Mead. Over the course of his career, Carver Mead gave us fundamental understanding of key semiconductor materials and devices. He pioneered the design methodologies and how generations of chip designers were taught, and also the automation tools that Dean Pisano mentioned, which chip designers have used as they built companies like Qualcomm or NVIDIA and AMD. Carver Mead also invented new architectures for computing. He worked out theoretical limits for computation that uses silicon. And he was the first to explore how biological and mathematical processes map onto the substrate of silicon. And here, I haven't even mentioned the most recent 30 years of his career. So of course, the best introduction to Carver Mead is through his own image and words. So let's enjoy this video that the Kyoto Prize organizers have prepared.
This is the Earth at night. And thanks to information technology, every human being in the world is connected to every other human being. And a more connected world is a necessary step towards a more enlightened world. Information technology, to most people, is this device. And inside this device, there's vastly more information processing than existed in the entire world when I started working on this technology. Well, VLSI stands for Very Large Scale Integrated Circuits. The integrated circuit is the engine which processes information. We all use information all the time. Images are information, and sounds are information, and drawings of buildings are information. But to get information from one place to another, or to figure out what to do from a drawing to make a physical object, we have to process that information. And processing information is done with VLSI circuits. And in 1959, Bob Noyce, who would later become a good friend of mine, figured out how to take one piece of silicon that used to hold one transistor and make an entire circuit with many transistors all connected together on that same piece of silicon. It was fantastic. How could you not fall in love with that kind of technology? I got hooked by Gordon Moore when he asked me, how far could it go? How many transistors? How small could you make them so you could put more and more on a piece of silicon? So I started working on that question, and it turned out, as you make transistors smaller, you put more of them on a piece of silicon, but each one takes less electrical current to run because they're smaller. And because the transistor itself is smaller, it takes the electrons less time to get through the transistor, so they're faster. Everything got better. So that meant that the problem wasn't how to make a better transistor, it was how do you make a thing that complicated, have it actually work. So the important thing was to take the concept that was in my head of what you wanted the system to do and translate that into physical form of an integrated circuit. I grew up in the mountains and spent a lot of time just walking out along the streams and in the trees. And when I'm not quite clear about something, I'll go out for a long walk. It gradually clarifies. There's something about nature that has a unity to it. The physics and the chemistry and the biology are all in the trees and the shore, and it's all one nature. If you think about the world we're in, we're accumulating new knowledge all the time. If you take that picture literally, the only thing you could ever do is to just make everyone more and more specialized. So you learn more and more about less and less, till finally you know everything about nothing. That's not where we want to go as a human race. There has to be someone thinking about what are the commonalities between all these different viewpoints? What is the essence of the learning that we're doing? When you get that, then you can see the field. You can see how everything works. This is what happened with my students in the VLSI course. They got to where they could see the whole thing, the essence of it, not all the detail. You can go back and get detail later if you have the essence, but it's hard to go the other way. As I can see the connection between work that I've done and the possibility of a device like this being developed. It's a very long trail of work by other people that linked anything I did and this device. But I'm still, every time I use this device, I have a warm feeling. There's part of me in it.
Seeking the essence and clarity, seeking to teach and enlighten. How wonderful and inspiring. Now, the symposium organizers once asked me to explain Carver's achievements, and I said to them that 3 words always come to mind. Physics, the laws that govern transistors or circuits or the universe. Simplicity, that distillation down to a clear essence. And scalability to millions or billions or an entire planet. Today, Carver will give us a talk on fundamental physical law. The title is Engineering Concepts Clarify Physical Law. So let's open our minds and pay close attention. And now let's give our very warmest welcome to Professor Carver Mead.
Good to be here today, and I'm especially pleased with the young people here just starting a career. I want to talk to you today, the rest of you. The rest of you are welcome to listen in, but I want to talk to the young people. My colleague, the late Richard Feynman, said something that I think captures what we're about in fundamental physical law. He said the real glory of science is that we can find a way of thinking such that the law is evident. If you look out on our discussions of fundamental physical law today, they're in the context of three great theories: electromagnetism in the form of Maxwell's equations, general relativity, which tells us all about gravitation, and quantum mechanics and its offshoots that tell us about stuff down at the bottom. When you look a little further at those theories, they're all over 100 years old. And we've learned a huge amount experimentally since they evolved in any meaningful way. So I want to share with you today some experiments, wonderful experiments that have been done, that to me make the law evident. So first of all, we should know what it means to be at the bottom. And quantum things are at the bottom level that we know about. And what does it mean for something to be quantum? It means just one thing. It means the wave nature of matter. And we're celebrating the 100th anniversary of that great insight by Louis de Broglie, 100 years ago this year. What's down at the bottom is not little grains of sand or little bullets. It's waves. So it's funny to be talking about waves in San Diego. But I mean a little more, something a little further down from what you could see. And I know a lot of you here are experts on that subject, but if you could just forgive me for a minute for doing a little primer on what waves are about. This is a view of a wave, and it's propagating from left to right. And I have it instrumented. So over here on the right, there's an instrument that measures the value of the wave coming out on the right-hand side. And down here at the bottom, it measures the amplitude of the wave looking at it from the side. And this is a small chunk out of a wave that's many, many wavelengths in dimensions crosswise. And what do we mean by all this? Well, the wave has a frequency, which we see. It's the rate at which this amplitude of the wave wiggles. And it has a wavelength. And so there's a vector that goes with every wave. The vector direction is obvious. The direction of propagation is perpendicular to the wavefronts, the way the wave is going. And the wavelength is just the distance it takes to go one wave down here, but the strength of the wave is actually how many waves there are per unit distance. And that's called the wave vector, or in ordinary units, it's called the momentum. So the rate at which the wave wiggles, its frequency is called energy when it's a matter wave. And the number of wavelengths per unit distance is called the momentum. And the momentum is a vector which is in the direction that the wave is propagating. Now, we're going to be doing some experiments with waves. The first thing you do is you put up something that stops the wave. This particular one absorbs the wave, so nothing gets through it, and nothing goes onto the other side, so you don't see any amplitude coming out here. But we can cut holes in it, and you can see the wave propagating, and you notice it doesn't keep going straight through like a little bullet would, and it spreads out from here. And if you cut 2 slots in the barrier, you get the famous 2-slit experiment. It's in all the textbooks about quantum things. And what you notice is that on the other side, there are angles like the straight through angle, which there are no waves on the left that go straight through, but the effect of these 2 waves adding up together has a maximum going straight through. And then you get off a little bit, and the distance from the top slot is just 180 degrees of phase, phase being a distance along the wave. It's just 180 degrees out of phase with the wave from the bottom slot. And so there's another angle. Go back to this one. So there's another angle here where you get a maximum. And in between, they interfere with each other. The 2 waves add up out of phase. And so the whole pattern here that you measure out on the edge is called an interference pattern. And we'll see a lot of those. The thing you notice about the interference pattern is this is a high frequency wave, and it's wiggling and fast. And this is the angle that it makes for the first maximum, aside from the one going straight through. But if I have a lower frequency wave, lower energy wave, longer wavelength wave, that angle's bigger. So it's wiggling slower, so it's a lower energy, longer wavelength, so it's lower momentum, and it has a bigger angle, and we'll see that. You can see it going back and forth between the top one and the bottom one. The angle to the maximum for the low frequency, long wavelength wave is higher than it is for the higher frequency, higher energy, higher wave vector, higher momentum wave. Now, of course, that all works in 2 dimensions as well. If you shine a wave through a crystal, you get maxima at these maxima in 2 dimensions. And here's the straight through one down here, and here's one where in both directions the things add up, right? And in 1927, just 4 years after de Broglie said matter was waves, the people at Bell Labs went and made a wonderful measurement, made a big vacuum arrangement, had an electron beam, and they found out that, sure enough, here's a electron beam that has 65 volts. That's 65 electron volts of energy per electron. And so the electrons bounced off the planes in the crystal, and the maximum, one of those bright spots in the maximum at 44 degrees. But if they lowered the voltage down to 54 degrees, then they found that spot went out to 50 degrees. So, sure enough, worked just like you'd expect for a wave that had a momentum, which was how many waves there are per unit distance, and had a energy, which was the frequency, how fast the thing wiggled. Well, 50 years later, there was a amazing experiment done. And I want to tell you about experiments that were done in the 60s and 70s, because the people that made up our great theories didn't see any of these. And these experiments tell us how the waves work. We already saw the first one that said that the energy of the wave changed its angle in just the right way. This experiment, a little bit harder to explain, but let me go through it because it's such a fundamental experiment. We'll need to understand it. This is a single crystal of silicon, which you could get in 1975, and they cut out chunks of it so that you had these three fins sticking up, and the fins are just thick enough so a neutron that's coming along, neutron wave, would have a straight through path here. That was the center spot that we saw, and has a spot off to the side, the diffracted spot that goes off at this angle. And now we have another part of the neutron. This is one neutron at a time. So the neutron wave splits into two. It's still the same neutron. Nothing funny about that. If it was a particle, that would be terribly, terribly disturbing. It's not. It's a wave. You can spread out if it needs to. This one felt like it. So here's the part of the neutron going this way, and now it gets diffracted again. And here's the straight through path, and here's the diffracted path. So I have that path, A, C, D, ends up at this spot on the right. And there's another path, the neutron goes straight through here and then diffracts on this one, A, B, D, and they both add up here at point D. Well, when they're adding up, they're either going to add up together in phase, means they're twice as big, or they can cancel out each other when they're out of phase. So the counts you get out here in these counters are going to reflect how the waves are adding up in or out of phase. And now the trick here, which was so beautiful, this whole thing is mounted in a metal box that's all nice and rigid so that you can rotate it around this axis shown here with the angle phi. And when you do that, you're in the Earth's gravitational field. So if you turn the thing clockwise like it's shown there, this part of the path up here, CD, is going to be higher in the Earth's field than path AB. And so the neutrons are going to have to, the ones that are diffracted here, are going to have to climb the hill of gravitational potential to get to the level up here at CD. Well, if they're going to have to climb the hill, their energy is conserved, and they have a kinetic energy coming in. That's why they're waving fast. So if they're going uphill, they give up some of that kinetic energy and turns into potential energy. So the gravitational potential higher up is higher. That means the kinetic energy is lower, which means it'll have a longer wavelength. So it'll get out of phase with its partner that came around ABD. And as you gradually rotate in the Earth's gravitational field, you see the waves adding up in phase here and out of phase here. This was a fantastic experiment. It directly shows that the neutron wave has, as a part of its momentum, the gravitational potential. And that's a thing we will see over and over again. Now, it gets better than that. If that was all there was, everyone would say that's obvious. But that's not all there is. You have two paths that the neutron splits into. So there's a path going around A, C, D, and a path going on A, B, D. And suppose I kept them flat with respect to the gravitational field, but I rotated them. Well, if it's the whole thing's rotating, then the neutron, the half of the neutron that goes A, C, D, has got further to go because it's got to catch up with D because the B has moved a little bit. And the one that's going this way, D has come a little closer, so this one will take less phase delay, and that one will take more. So there should be a vector effect. Well, what would the vector effect come from? Well, if you're in the frame of reference of the neutron, there's a big universe out there. And the matter in the universe, the effect on the potential goes like 1 over the distance, but the amount of matter goes like the square of the distance. So the effect on us of matter out in the universe gets bigger as the matter is further away. So most of the matter that affects us here when we do our experiments is very far out in the universe. Well, they did that experiment. How are you going to arrange it so that you can rotate it so smoothly that it doesn't, it's got a big effect of the Earth's gravitational field. How are you going to get rid of that? Well, what they did is they mounted it on a post like this, and they could still turn it around. But if the perpendicular here to this ABDC plane is got a projection on the rotation of the Earth, you just let the Earth turn it around. That's nice and steady as it gets. And if you have it turned one way, if the perpendicular to that plane is aligned with the rotation vector of the Earth, then you'll get a phase shift in one direction. And if you turn it 180 degrees so that the perpendicular is anti-aligned with the Earth's rotation, you'll get the opposite phase. Well, they did that. And here it is right here. If you point the vector north, it's aligned with the rotation of the Earth, and you get a positive phase shift. It's not quite a full cycle, but it's 100 degrees. And if you point the thing west, then the thing is just goes around, but it doesn't rotate. So it doesn't register any phase shift. And then if you have a thing back up the other way, then it's rotating the other way as the Earth rotates relative to the distant universe. And so, in fact, in a very rough way, we've established that this neutron wave, the vector part that's directional, knows where the universe is. Well, that's a direct message from the neutrons. It's telling you, it's making its law evident. Well, not many of us can afford a source of neutrons, and the setup itself was pretty complicated, so we're not going to have one of those in a freshman physics lab. But there are things we could do in a freshman physics lab that tell us just as clearly what the wave nature of matter is doing. Now, you've all seen pictures like this. First thing you learn about electricity is you take a battery, has some voltage, and you hook it up to a chunk of something or other, and it makes a current go through there, and the current is proportional to the voltage divided by the resistance of the stuff. So it resists the electrons flowing. And that means the velocity of the electrons is linear in the electrical field pushing on them, and they go at a distance. That's 1,000-year-old thinking. That's the way they used to think mechanics worked. You had to push something along to keep it moving. And it wasn't until Galileo had his nice marble slabs that he showed that it still had its kinetic energy that came from the potential energy of letting it roll down a marble slab. So what have you done to the electrons? You've put them in something that completely scatters their wave nature, makes it all random. And so they can't propagate in a nice way that electrons want to do unless you mess them up. So a horrible way to learn about what electrons are like. The electron its acceleration should depend on the electrical field, not its velocity. Well, turns out that's what happens if you make an environment for the electrons that doesn't mess them up. That was first done in 1911 in Leiden, just a little town south of Amsterdam. And a guy by the name of Camerlingionus. And he was dutifully measuring Ohm's law here. Here's a resistance in ohms, that's that omega there, and that's very low. You can see it's a 0.15 of an ohm. And this is a wire of mercury. Mercury, of course, is liquid metal at room temperature, but you can make it in the shape you want and then cool it and turns it into a solid. So it's very convenient to use for low temperature measurements because you can make any ring shape you want. And he noticed that he was coming down here, cooling. He was the first guy that figured out how to liquefy helium, which happens around 4 degrees absolute. And so he was bumping on his helium here, making it colder and colder, and bang, the resistance went away. Well, of course, he figured out something in his setup had broken. The voltmeter wasn't hooked up anymore, and so he was hunting around trying to figure out what had gone wrong. In the process, he wasn't pumping so much on the helium, and it started to warm up a little, and bang, the resistance came back. Well, he's a smart guy, so he said, if I can go back and forth reproducibly, that means it's a real physical effect. But it gets to a resistance which is way lower than anything I can measure. So what do I do? How would I find out what it is? Well, a smart guy, he said, I'm going to take the mercury and I'm going to make it into a ring. This ring here, it goes underneath this apparatus there. So that's a continuous ring of mercury that ain't cooled down. And he found a way to, he reasoned like this. If I can get a current started in the ring, it'll make a magnetic field, and I can tell if there's a magnetic field there by putting a compass down there. They're ordinary, old-fashioned magnetic compass. So he did. He got the thing superconducting, he got a current started in it, and the compass went from pointing north here to pointing east. And he expected it to die out within seconds or maybe minutes. He kept pumping on his helium overnight, and it was still going just as strong. The most significant physical experiment ever been done. This is perpetual motion. Never been anything like that. There, to this day, isn't anything like that. It's a perfect frictionless system. Well, people puzzled over this, and then a couple decades later, the London brothers said it must be a coherent quantum system, a macroscopic quantum system, because that's the only way it could work. Because if it's a quantum system, it's a wave, and the wave goes around, and it has to come back in phase with itself. So unless you break it, and there's 10 to the 23rd electrons in it, and so the little thermal wiggles that happen at 4 Kelvin aren't going to do anything to something with 10 to the 23rd electrons in a coherent quantum state. Macroscopic wave of matter. Unbelievable. This teaches us about matter waves in a way that nothing else we've ever had can do. Well, it took another 50 years. It's astounding. This is an experiment Onus could have done and didn't think of it. There's a group in Germany and another group in Stanford here in California did. Their findings were published in the same issue of the Journal of Physical Review Letters in 1961. And what they did is they had this is a little ring. They used lead. Lead's a good superconductor too. And they found a way to trap current in it when it went superconducting. And then once it had a little current in it, instead of using a compass, well, a compass is a big clunky thing, but you do the other thing. You turn the little current thing, you hang it on a spider web so that it can rotate with a very little bit of force, and you put a very weak magnetic field on it. So you've turned the sample itself into the needle of the compass. So it's not so different from Onus's measurement. And how much that angle changes as you put the little very weak magnetic field on from outside tells you what the magnetic moment is. Well, what's a magnetic moment? Well, this tells you in a way that's evident. The magnetic moment is the wave comes around in phase with itself. Well, that can be in phase with no phase change around the loop, or with one cycle phase change around the loop, or with 2 cycles phase. That's what these are. The flux is quantized. The magnetic moment is quantized. What that is the wave vector of the electron condensate, this magic, perfect, frictionless phase of matter. The phase comes around, and it must come around in phase with itself. And that phase is quantized. So this is where the term quantum comes from. It's the reason that the energy levels of an electron, a single electron in an atom, comes around in phase with itself. And that gives it can be 1 phase, 0. No, electron can't be 0 because it's got this complicated thing called spin that we still don't understand very well. So all of the quantum levels of things come about because matter is waves. And the waves have to come around in phase with themselves. Well, that last experiment could have been done by Camerling Onus, and you can certainly do it in a freshman physics lab. Here's another one you can do in a freshman physics lab. The Londons predicted if you had a ring of superconductor and you spun the ring, you would get a magnetic field. What in the world is that about? Here I have this frictionless stuff, and it's in a ring that has positive charges because, of course, those electrons came with the atoms that made the ring, and they just happened to get free and gang up and make this wonderful condensate. And that's a frictionless thing, but there's still a positive charges there. So when you spin the ring, you have the positive charges go around. Well, now if the electrons would go exactly with the positive charges, there wouldn't be any current, because electrons going that way would be a negative current. Positive charges going that way would be a positive current. They cancel out. But that's not what happens. As you spin the ring faster, the magnetic flux gets bigger. What in the world is that about? I have a perfect electron condensate, frictionless, and it's got no flux in it, no twist in its wave function as it goes around. So the wave has the same phase all the way around. Now, what's in the world is it doing that it becomes a magnetic field? Well, think about it this way. If I start the ring rotating, I start the positive charges, the electron condensate is a free-floating thing, but it feels the magnetic vector coupling with the positive charges going around. So it has to speed up to keep up with the positive charges. Well, you would think then it's perfect, so it ought to just keep up perfectly. Well, it doesn't. It lags behind. So as you accelerate to make the ring spin, it has to accelerate relative to the universe. So when you're not moving, you're not spinning the ring relative to the universe, there's no magnetic flux. The electrons are perfectly lined up with the positive charges. But when you spin them, there's no mechanical coupling. The condensate is a perfect thing, but it's charged and it has mass. It has the quantity of matter that couples gravitationally. So this is a perfect experiment that has the vector coupling of the positive charges moving, which we call magnetism. And it has the vector coupling of from the point of view of the electron condensate, it's the universe out there going around. So it induces what we call inertia in the matter. And here's a perfect example where there's no friction to get in the way. And this can be done in a freshman physics lab. Well, those are experiments that make the law evident. What about light? Light's just one way of a matter wave one place that's charged, talking to a matter wave someplace else that's charged. Maybe it will have some coupling to gravitation. It's funny, Einstein struggled with this question, never quite settled to the end of his life. In 1911, he had a wonderful, simple, clear theory where the velocity of light was a function of the gravitational potential. Interesting. Then in 1915, he crafted, with a lot of help, a very much more complicated and very much more obscure theory of gravitation called general relativity. And general relativity has two things. It has an equation, a sort of wave-like equation for the gravitational potential, which is reasonably easy to understand if you take the simple case. And it has a stipulation that you guess what function light speed is of the gravitational potential. And that's something you have to put in addition to the theory. It's just the math doesn't tell you that. You just have to guess it. Well, he changed his mind and he guessed that it was going to be independent of gravitational potential. And that statement, that choice, has doomed us to work in curved space-time ever since. So if you put matter in your space, a meter isn't a meter anymore. It's a nightmare. You can do it. The smartest people in the world I know have made that work. But you have to change the coordinate system in order to do it. From the coordinate system that says light is constant speed no matter where you are in a frame of reference which isn't accelerated or rotating. Well, let's look at what, I'm an engineer. Let's do the measurement. Erwin Shapiro in the late 60s was at MIT, and they had an old radio astronomy antenna there that wasn't used very much. It's called the Haystack Observatory. And he was good at doing experiments, so he put together a real high power radar. He had the antenna, you shoot out a microwave signal out of the antenna and you'll wait for an echo to come back. And he got good at getting echoes from Mars and Venus. Well, Mars and Venus have their inner planets, so they have faster periods than the Earth. And so when we watch them, they occasionally go real close to the sun. And so when they do, he measured the delay. And there's this huge increase in the delay when the radar signal goes next to the sun. And guess what? It's exactly the form that you would calculate if the speed of light was proportional to the gravitational potential. Very interesting. Now, you can either calculate that curve the hard way by assuming the speed of light is constant and then changing into a coordinate system where it's doing what it's doing, really and physically. Or you can just say, I'm going to work in the system where it's doing what it's doing. Makes everything a lot simpler. So we've discovered that light has an effect on gravitation, or said the other way, gravitation has an effect on light. This is a scalar effect. So gravitational potential changes the speed. Then if all is like the neutrons, should have a vector effect. Well, guess what? Right now, inertial navigation is not done with old mechanical whirling gyroscopes anymore. It's done with fiber optic gyroscopes because you can start light. This is a wonderful device. You start with a laser, and this thing called B here is a beam splitter. It spits half the light off at 45 degrees, and the other half goes straight through. So this beam comes in, it goes up, Half of it goes up, half of it goes straight. So now we have two halves of the light beam going in opposite direction around these many turns of the coil. And when they get to the other end, they come back and they combine here. The one from the top goes straight down. The one from over here bounces off and goes down. And so they add up at the detector, just like the neutrons did. And guess what? You get a really nice pattern, an interference pattern, if you rotate this. So you can buy these things. Here's a commercial one that has one coil of fiber optic. It's just what's shown here. And this is a complete 3-axis gyroscope. So it has 3 of these things that mounted on 3 orthogonal axes. And so what you can do is you can put this on your the mounting surface of your astronomical telescope. And it has motor drives, so you can tune the motor drives until all 3 axes read 0. And then you go look through your telescope. And the distant galaxies are stationary. Don't try to tell me that's an accident. That's the vector coupling of the distant universe. Well, you've all been told that there is no preferred frame of reference. And that's just wrong. Looking at the experiments, it's clear there is a frame of reference, and that's the distant mass in the universe. Well, then how can special relativity work? Einstein made very clear, if you're moving in a straight line, not rotating and not accelerating, you can be any velocity in any direction, and you get an equivalence in the results that you get in a local experiment. How can that possibly be true when we're moving in a vast potential of the universe? Well, let's look at the universe. We're living in an accelerating universe. And by now, we know a lot about that by observing. And one of the things Hubble figured out in 1922 is that the things furthest away are moving away from us the fastest. That's Hubble's law. Well, if you take that literally, you go further and further, and finally you get to where they're moving away from us at the speed of light. Well, that means that we can't see them anymore. Light can't get back to us, and gravitational interaction can't get back to us. So that means that all cosmologies have a horizon. It's that distance when the stuff is moving away from us at the velocity of light. Well, what does that actually mean? Well, what it means is if I look in any direction, the stuff's moving away, and it looks like its furthest stuff is moving faster. Well, suppose I'm moving towards one of the horizons in a straight line, not accelerating. It means that horizon moves away from me. I'm catching up with the matter. So the horizon moves away from me, and the one behind moves it. So it means that the effect of the universe, as long as it's pretty much the same beyond the horizon as it is this side of the horizon, it means that if you're moving at any velocity, the horizon just moves around a little bubble with you. That's why special relativity works. It's not just a mathematical thing, it's physics in it. Coupling with the universe that's moving away, and most of it's moving at near the velocity of light, then you get that the local experiments don't know about moving in a straight line because the universe that you can feel and see moves with you. It all makes sense. It's a way of thinking that makes a law evident. So let's think about the history of the universe. It started out much denser than it is now. And so it had a lot of kinetic energy. Otherwise, it wouldn't be continuing to expand. But gravitation is an attractive thing. So it means that to separate matter takes energy. So as you're separating the elements of matter, like they have little rubber bands between every two elements of matter, and as the universe expands, it's stretching those rubber bands. The gravitational potential is that gravitational potential due to the attraction of all matter with all other matter within the horizon. That's the potential of every element of matter. Guess what? Einstein said the energy is mc squared. That's the rest energy of matter. 100% of that rest energy is gravitational potential. And every element of matter has inertia. You have to put energy in to accelerate it. 100% of that inertia is a gravitational vector coupling. So if we just take what the universe is telling us, the laws, the fundamental laws are evident. Now I'm talking to the young people here today. You won't hear this very many places. But compared with wading through the layers and layers of opaque mathematics in the three great theories that are out there, it's vastly easier. You can do everything I've talked about today with trigonometry and first-year calculus. You're the ones that can find a new way of thinking and turn it into a real theory that makes real predictions. One of the things you'll find right away is you see questions that make sense in this way of looking at it that you can't even ask in the traditional theories. To try to find something new to do with the traditional theories, 100 years of the smartest people in the world working on them, they've worked most of the problems. Not much left for you to do. You look at things in a new way, there's a huge number of things we don't understand, but the big theories shield them from you. In quantum mechanics, when you ask about, well, what makes the wave function collapse? They say, oh, you can't ask that question. I remember being told that when I was an undergrad. I said, what do you mean I can't ask that question? I just did. Well, you can ask questions. You can become leaders in learning about the results of looking at physical law through the eyes of these wonderful experiments that make the laws evident. So go out there and do it. Bless you.
I don't know about you, but my head feels stretched. Maybe my head is dense because I'm old, and when I tried to pack more stuff in, it got a little more crowded. But I have to say, in my 41 years in academia, this is the first time I heard someone give a coherent call to action to all the young people in the university, to all the young people who have the obligation to revitalize the university, to go ahead and make that revitalization. Dr. Carver Mead, I am totally blown away, and I'm just honored that I was able to be here with you when you made that call. I'm truly, I'm not on the script, I'm just emotionally blown away by it. So I just wanted to offer that heartfelt thanks. Thank you very, very much. I think we're done. And I don't know about you, but I'm not going to look at a magnet the same way again, ever again. Thank you.